Hello friends, today we shall derive an expression for series combination of capacitors. Combination of capacitors means grouping of capacitors. Capacitors can be combined or grouped in two ways. They are series combination and parallel combination. And first one is series combination of capacitor. Series combination of capacitor. Consider two capacitors of capacitances C1 and C2. Let C1 and C2 be the capacitances of two capacitors, and they are connected in series. The series combination in which the capacitors are connected end to end. One end of capacitor is connected to another end of the capacitor, another capacitor, and the combination is connected with a battery or cell of potential difference phi. Let phi be the potential difference across this combination, and another plate of capacitor is connected to second. First plate is connected to second plate of second capacitor, and second plate of first capacitor is connected to first plate of second capacitor. This is series combination. Series combination of capacitor. And let Q be the charge sent by the battery or cell, and it is stored on first plate of the capacitor. Charges are stored inside the capacitor. This is Q charge, and negative charges are induced on the second plate of the capacitor. And now these two capacitors are isolated and they are connected with a wire. Therefore, if it is negative charge minus Q, then charge on first plate of second capacitor is also positive. Therefore, here positive charge Q is on first plate of capacitor, then minus Q will be on the opposite plate of this capacitor, and positive charge on the plate of a capacitor is called charge on capacitor. Therefore, charge on first capacitor is Q. The charge on second capacitor is also Q, because positive charge on the capacitor plate of a capacitor is called charge on the capacitor. Therefore, from this it is clear that charge on each capacitor remains same. That means if the capacitors are connected in series, charge remains same on each capacitor. If 3 capacitors or 4 capacitors or n capacitors are connected in series, the charge Q remains same when they are connected in series, and the potential difference, that is phi, is divided. Potential difference divides, and total potential difference across the combination is applied potential difference is phi, and this phi equal to phi1 plus phi2, where phi1 is the potential difference across C1 and V2 is the potential difference across C2. And we know that C equal to Q upon V. This is capacitance of capacitor. C is the capacitance, Q is the charge stored by the capacitor, V is at potential difference. Hence, C equal to Q upon V. Therefore, V1 is equal to charge on first capacitor is Q upon its capacitance is C1. Therefore, V1 equal to Q by C1 and V2 is equal to charge on second capacitor is same Q upon its capacitance is C2. Therefore, V1 equal to Q by C1 and V2 equal to Q by C2. Therefore, total potential difference or net potential difference across the combination is V, and that V equal to V1 plus V2, where V1 equal to Q upon C1 plus Q upon C2. From this equation, or consider this equation 1. From equation 1, V equal to Q upon C1 plus Q upon C2. Consider this as equation 1. Now, this combination is replaced by an equivalent capacitor of capacitance CS. Consider a single capacitor having capacitance CS. CS is suffix CS. Equivalent capacitance in series combination, or you can represent as CE, equivalent capacitance of two capacitors. Or better it is CS. CS is equivalent capacitance in series combination, and if this equivalent capacitor is connected across the same potential difference V, then the charge stored by this capacitor is plus Q by first plate and minus Q on second plate. But the positive charge on the capacitor is called charge on the capacitor. Charge on the capacitor. Now, according to C equal to Q upon V, where V equal to, therefore, net potential difference across this single capacitor V equal to charge stored is Q and its capacitance is CS, where CS is equivalent capacitance. Consider this as equation 2. Now, equating equations 1 and 2, left hand side are V equal to V. That means it is the same potential difference and charge stored is the same. Therefore, from equation 1 and 2, or equating equation 1 and 2, this V equal to, this V can be written as Q upon CS, and Q upon CS is equal to Q upon C1 plus Q upon C2. Here Q is common and this is Q. This Q and this Q get cancelled. Remaining 1 upon CS is equal to 1 upon C1 plus 1 upon C2. This is the expression for equivalent capacitance of two capacitors in series. And for three capacitors, if three capacitors of capacitances C1, C2, C3 are connected in series, then 1 by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3, so on up to n. 1 by C4, 1 by C5, so on. Clear? And for two capacitors, equivalent capacitance in series combination can also be written as Cs is equal to C1 C2 divided by C1 plus C2. Here LCM is C1 C2, and in the numerator this is definition of C2 plus C1, or C1 plus C2 divided by C1 C2, that is equal to 1 by Cs, and reciprocal of it is Cs equal to C1 C2 upon C1 plus C2. Clear? And now if two capacitors of same capacitance C are connected in series, that means for C1 is equal to C2 is equal to C. For same capacitances, two capacitors of same capacitance C are connected in series, then equivalent capacitance of two capacitors of same capacitance are Cs equal to, here this is C into C, C square divided by C plus C, 2C. C square divided by 2C equal to C by 2, that is C square upon 2C. C get cancelled, C divided by 2. C divided by 2. If three capacitors of same capacitances are connected in series, then C by 3. Four capacitors are connected in series, then their equivalent capacitance is Cs equal to C by 4. If n capacitors are connected in series, then Cs equal to C by n. Thus, equivalent capacitance of capacitors in series is always less than the smallest value of capacitor connected in series. Clear? And for series combination, charge on each capacitor remains the same. If you connected a large number of 10-15 capacitors, then charge on each capacitor remains the same, but potential difference divides, that is phi equal to phi1 plus phi2 plus phi3 plus phi4 plus so on, how many capacitors are connected. Okay. Now we shall solve a problem on this. Example, two capacitors 4 microfarad and 2 microfarad. Two capacitors 4 microfarad and 2 microfarad are connected in series across a cell or battery of terminal potential difference 12 volt. Therefore, here given C1 equal to 4 microfarad, C2 equal to 2 microfarad and phi equal to 12 volt. Then find charge on each capacitor. Charge on each capacitor. First find equivalent capacitance. Find equivalent capacitance. Equivalent capacitance in series is given by Cs. Number 2, charge on each capacitor. Number 3, potential difference or Phi1 and Phi2. Potential difference across each capacitor. And energy stored by the combination energy stored by the combination of capacitors. And by 2 microfarad capacitor. Now, if the capacitors are connected in series, then their equivalent capacitance is given by a single capacitor. Therefore, this circuit can be reduced to a single capacitor of capacitance Cs, and it is connected across the same potential difference 12 volt Then what is equivalent capacitance? Number 1, equivalent capacitance. Equivalent capacitance Cs equal to, according to the formula, C equal to Q by phi. Q by phi. Here you know C and phi, then Q can be calculated. Equivalent capacitance, first we calculate equivalent capacitance, and equivalent capacitance for two capacitors is given by Cs equal to C1 C2 upon C1 plus C2, or 1 by Cs equal to 1 by C1 plus 1 by C2. Therefore, for two capacitors, Cs equal to C1 into C2 upon C1 plus C2. That is equal to, here C1 is 4 microfarad, C2 is 2 microfarad. That is 4 into 2, 8 into microfarad, 10 raised to minus 6 into 10 raised to minus 6 equal to 10 raised to minus 12 divided by C1 plus C2. 4 plus 2, 6, and here 10 raised to minus 6 is common. Micro is 10 raised to minus 6, and that is equal to 8 upon 6 equal to 4 upon 3 into 10 raised to minus 12, it is into 10 raised to plus 6, that is equal to 10 raised to minus 6, or 10 raised to minus 6 can be written as microfarad. Therefore, equivalent capacitance of two capacitors 4 microfarad and 2 microfarad is 4 upon 3 microfarad, that is equal to 1.33 microfarad, and it is less than smallest value of capacitance. Clear? Next, number 2, charge on each capacitor. here what is the charge on this capacitor? We know that charge Q equal to C into P, that is CS into P. Here CS is known, that is equal to 4 upon 3. This is a single capacitor and CS is its capacitance. It is connected across 12 volt battery. Therefore, charge stored by this capacitor is Q equal to CS into V, C into V, and CS equal to 4 upon 3 into 10 raised to minus 6 farad, microfarads, and into 12 volt. Here 3 ones are 3, 4s are 12. 4 into 4, 16 micro coulomb charge is stored by a single capacitor. And according to the law of series combination of capacitors, same charge is stored on each capacitor. The charge stored by this capacitor Q is equal to charge remains same. Therefore, charge on each capacitor is 16 micro coulomb. Therefore, charge on each capacitor is equal to 16 micro coulomb, and equivalent capacitance is 4 upon 3 what is farad, microfarad. It is the equivalent capacitance, and charge on each capacitor is 16 micro coulomb. 16 micro coulomb. It is also 16 micro coulomb. Then potential difference across each capacitor. Potential difference across each capacitor. Number 3, potential difference. We know that P equal to Q upon C. Therefore, potential difference across first capacitor is P1, and P1 equal to Q upon C1. Therefore, potential difference P1 equal to Q upon C1, that is Q equal to 16 micro coulomb divided by C1 equal to 4 microfarad, and that is equal to 4 ones are 4, 4s are 4 volt. If 4 volt is the potential difference across first capacitor, then we know for series combination P equal to P1 plus P2, P equal to 12 volt, 12 minus 4 equal to 8 volt. Therefore, V2 should be 8, or V2 equal to charge is same Q upon C2, and C2 equal to 16 microfarad divided by C2 equal to 2 microfarad. 2 micro coulomb, it is microfarad. That is equal to 2 ones are 2, 8s are 8 volt. Therefore, potential difference across first capacitor is 4 volt. Potential difference across second capacitor is 8 volt. 4 plus 8, 12 volt, or 12 minus 4, 8 volt. Therefore, potential difference across capacitor first is 4 volt and second capacitor is 8 volt. Hence, potential difference across each capacitor is V1 equal to 4 volt and V2 equal to 8 volt. As capacitance decreases, potential difference increases. Potential difference increases since C equal to Q by phi. As phi increases, capacitance decreases, or phi equal to Q by C. As C increases, phi decreases. This is the potential difference across each capacitor. Then energy stored by the combination of capacitors and energy stored by 2 microfarad. Clear? Now, energy stored in a capacitor is given by energy stored in a capacitor is U equal to half CV square. We have derived it. Energy stored equal to half CV square, or Q square divided by C, Q square divided by 2C, or half Q into V. You can use either of the expression. Clear? Therefore, U equal to, here for combination equivalent capacitance is CS. Hence, energy stored in combination of capacitors, U equal to CS into phi square. That is equal to half CS equal to 4 upon 3 into 10 raised to minus 6 into phi square, where phi is 12 volt. Therefore, 12 into 12 phi square. Here 2 ones are 2 twos are 3 ones are 3 fours are 12 into 4 48 into 2 96. Therefore, energy stored in the combination of capacitor is 96 into 10 raised to minus 6 joules. Unit of energy is joule. Here 10 raised to minus 6 is micro. Hence, it can be written as energy stored by the combination of capacitor is 96 micro joule. 96 micro joule. And energy stored by 2 microfarad capacitor. 2 microfarad capacitor. And for 2 microfarad capacitor, suppose this is the 2 microfarad capacitor, its capacitance is 2 microfarad. What is the charge on this capacitor? That is, each capacitor is 16 microcoulomb. Therefore, Q equal to here 16 microcoulomb. Then what is the potential difference across 2 microcoulomb? That is phi2 equal to 8 volt. Here for 2 microcoulomb microfarad capacitor, C equal to 2 microfarad, Q equal to 16 microcoulomb, and phi equal to 8 volt. Then energy stored U equal to, you can use half CV square, half C into V square, or Q square divided by 2C or half Q into V. You can use either of the expression, then you will get the same answer. Therefore, U equal to, we use here half CV square, and that is equal to 1 upon 2. What is C here? That means C2. 2 into 2 into 10 raised to minus 6 farad into V. V is 8. Therefore, V square equal to 8 into 8. Here 2 get cancelled. Remaining 8 into 8, 64 into 10 raised to minus 6 joules, or that is equal to 64 microjoules energy stored by 2 microfarad. Then what is the energy stored by 4 microfarad? Total energy stored is 96 microjoule, and out of 96 microjoule, 64 microjoule is stored by 2 microfarad. Then 96 minus 64 is equal to 32, and 32 microjoule is stored by 4 microcoulomb. That means as capacitance increases, energy stored decreases. Capacitance for smaller charge, energy stored is larger. Clear? Thank you. In next class, we shall derive expression for parallel combination of capacitors.